Okay. So today's lecture is mainly focused on dry docking, but there is a small section on that trimming that I have to finish. It'll take some 10 minutes. I'll just finish it off, and then we will go into what is called dry docking. So what we are left with is that we said that we can have trimming aft and trimming forward. Now, as a result of that, we can have I told you that the change of draft can always be given by W by TPC, which is the parallel sinkage, plus or minus or plus the L into W into D, and not this L, small l into W into D divided by capital L into MCTC. So, this gives you the total change of draft as a sum total of the weight by TPC and that is parallel sinkage and the trimming. So, that the two of them gives rise to the total draft. Now, usually there is a way of writing trims, means you have the trims at different what we say is that, see, the trim will change as a function of the weight of the or the cargo that is added to the ship. Now, so what we usually do is we can say that this is the trim for a unit weight. Okay, we write in terms of, now trim depends on a lot of factors, as we have seen. One of the factors, as this equation we have given below shows, that is that W by TPC plus this thing, it shows that it is a function of W, okay, right. It is a function of W here and here. So, it is directly proportional to W. In fact, the total cargo that is in the ship, that it is proportional to that. So, one simple way of writing this system would be that you can write in terms of unit weight, what we call as, okay. So, what we call as unit weight here is it is just a nomenclature, I mean it is just a convenience. We call 100 tons as unit weight. So, first we give we can give a table for all the trim values for, means trim, as you can see, it depends on many other factors as well other than the W. It depends on all the as the draft itself as you know that as the draft changes, means as the ship keeps sinking, MCTC actually will change. Though I have said it to be a constant, it actually changes with draft. Means usually we talk about draft in the range of, let us say, few centimeters. So, probably MCTC does not change, but when there is a big change, see, these tables are usually it is called actually a trim table. So, these tables are usually made for a very large variation of draft. You start from a draft of, let us say, the whole weight, the whole height of the depth of the ship is probably 8 meters, means you start from 4 to probably 7 meters, like that, okay, draft. So, in steps of 10, that is how a trim table is made. Now, the table is actually I cannot show you right now, because in the computer I do not have that complete form of the trim table, but it is called a trim table, and it is usually written like what is the trim at a particular draft in certain particular conditions for unit weight. It is written in terms of unit weight. The advantage is that if you want to calculate for any particular weight, let us say 400 tons, all you need to do is multiply this draft with 4. This is for 100, as you can see it is directly proportional to W. So, all you need to do is multiply it by 4, and therefore, you will get for 400 tons 350, you multiply it by 3.5, like that. So, this is one way of for instance, let us look at this problem. It says that it says that suppose that there is a ship which has a displacement of, these are the particulars of the problem, a ship has a displacement of 35,000 tons and the length of the vessel is given to be 174 meter. Now, you are asked, okay, what is the change of draft if 400 tons is added 120 meters forward of AP. Now, the same problem given here, you can write it in the same thing, okay, this thing you can write it like this. See, the change of draft is equal to W by TPC plus this. Now, if you write it in terms of unit draft, this becomes, we will call it 1 for the time being, okay. When it is 1, this also becomes 1. Now, see, it becomes 1 by TPC. 1 by TPC is like a constant for a, it is true that for when the draft changes, the TPC can change, it is happens, but that is not needed because we are talking about change of drafts of probably a few centimeters. So, it is okay. MCT, so we will assume that for this course, I think you can assume that MCTC and TPC are constant for a ship, okay. It is okay, I think it is okay, but just know that it can change with the different drafts, it can change. So, this 1 by TPC is like a constant, let us call it K0, it is some constant, plus this L is the distance between the aft perpendicular and the center of flotation, we have already defined that. Capital L is the length of the ship, MCTC is the moment to change. Now, all three are again constants for a ship. So, we can write this as K1 into D. D is the distance through which the weight is moved, or I mean, yeah, that is the distance through which the small weight W is moved. Now, therefore, you see that the change of draft can be written as K0 plus K1 D. Note that this D is usually measured as the distance from the center of flotation, okay. Again, that I am just repeating it. So, this change of draft can be written as change of draft is equal to K0 plus K1 D, where K0 and K1 are constants and the only variable is D. Therefore, it is a linear variation with D. Now, this is actually the change of draft aft. I mean, I have done this. If you use the small l, it is actually change of draft from aft side, okay. If you want to find the change of draft forward, you have to use it will be this W by TPC plus L minus L, okay, into W into D by L into MCTC. This is very similar to what we described for a change of trim, that also the same formula comes. So, W by TPC plus this will give you the change of draft forward. Okay, so, this is the expressions for this. Also can be written as K0. I mean, if you are writing in terms of unit draft, I mean unit weight, it becomes 1 by TPC plus L minus L into D by L into MCTC. So, K0 plus K2 into D, this can be written in the same thing. This is forward, that is aft. Now, in this particular problem given here, displacement is given as 35,000 tons, this is given. Now, you are told that 400 tons is added 120 meters forward of AP, and you are asked what will be the change in draft. Okay. Now, if the weight is loaded, okay, D, small d is the distance through which the weight is moved, or it is also the distance from the center of flotation of the point where a weight is added, okay. It is two ways, it is the same thing. Now, if the weight is added at the forward perpendicular, the distance D becomes, this is how you look at it, that is, if it is at the forward perpendicular, distance D will be the distance between the center of flotation and the forward perpendicular. So, the center of flotation position is given in the actually, though I did not mention it, LCF position is given. So, you will get something, and similarly if the weight is added at the aft perpendicular. So, this D is the distance between the forward perpendicular and the center of flotation, this D, and this D will be the distance between the aft perpendicular and the center of flotation. Now, what you can very simply do is you have to find the, in this problem 400 tons is added at some point in the forward perpendicular, some point position of forward perpendicular. What we do is we can do is first we can find for unit weight change, and finally for 400 tons we can just multiply it by 4. Okay. So, we will do that. First of all, you need to find K 0, that is the, we defined it as W by TPC, calculate that. Then similarly K 1, which is L into L by L into, what was the formula, L into D, L into D by L into W into D, this is for unit weight. So, K1 is equal to L into W into D into D, okay, okay. K1 is just L. So, this is for unit weight. So, it is L by L into MCTC. So, this will give you K1, and similarly K2 will give you L minus L, but though we called it as unit weight, W is 100 tons. So, that needs to be put, as you said, W should be put 100 tons. Okay. So, because it is unit, we called it unit weight, but it is not 1 ton, it is actually 100 tons. So, that 100 has, it is to be multiplied with 100. So, 100 here into 100 tons divided by L into MCTC. So, this will give you K1 K2. Now, what we do is if you are, now let us find the aft region. Okay. Let us find the change in the draft aft. So, loading, now if you load at forward perpendicular, the change in draft aft, change in draft aft will be K 0 plus K 1 D, which is equal to K 0 we have calculated plus K 1 into, the only thing is D. You have to calculate the distance between the center of flotation and the forward perpendicular, and so that will give you some. Now, note one thing, when you are doing this, I mean this is very it's, I mean everybody knows, but still one side means when you are taking the distance from forward perpendicular, when you take 1 D, the forward side you take it as positive, and the other one you have to take it as negative, because see this is 0, center of flotation is 0. So, one side is positive, one side is negative, whichever way, this side is positive, that side is negative, or that side is positive, which, but at any rate one side should be positive and one side should be negative. So, one of them will have a K1 D, D will be positive, and in the other case then change of draft now this is if you are loading at the forward perpendicular. If you are loading at the aft perpendicular, change of draft will be K 0 plus K 1 into D, but this D will be, if this is positive, this will be negative. Okay. So, we are considering two cases. What is the change in the draft in the aft side? If you are, there are four cases here actually. First, there is a change in draft aft, there is a change in draft forward. Now, for each of these there is a change in draft due to loading at the forward perpendicular, loading at the aft perpendicular. So, 2 into 2, 4 cases are here. So, in the aft you have loading at forward perpendicular, there will be a change of draft aft, which is given by K 0 plus K 1 D. When it is loaded at the aft perpendicular, you will have change of draft will be K 0 plus K 1 D, but it is the new D, it will be a negative D. Similarly, you do the same thing for forward. Now, now the only, okay, now this is, see now we have actually four cases I mentioned, 2 for aft, 2 for forward. Now, actually for unit, now we can make a kind of straight line, that is for any one of these cases we can say that if the weight is loaded at any point in between, you can it will be somewhere in that straight line, right. Means we have d here, it is a straight line. So, all you need to do is change that d, it becomes a straight line, it will be somewhere in that straight line. So, if you any point, if you just draw that straight line between the aft and forward, like d can vary from this minus which is the aft point and plus that is a maximum point. So, that d variation Now, just draw a complete graph, and what you can do is, if you are told it is loaded at some point, you just look at that distance from the center of flotation, whether it is forward or aft, and then you just choose in that graph, that is all. So, it becomes that graph in a way is like the trimming graph or the trimming table, the table associated with that is called the trimming table, and so it is drawn for unit draft. So, two things you have to do later. Once you have the trimming graph or the trimming table, you just look at the table, and first you will see what is the d, okay, d, and you will directly read from that, for that particular d what is the draft, and number 2 is you have to multiply by the weight. This is for 100 tons. You have said that in this particular problem 400 tons is added, therefore, you just multiply it by 4. So, two things when you, so see we have here the load, you have two equations. Similarly, you have 4 equations. This is in the aft side, similarly in the forward side. So, totally 4 equations, K0 plus K1d and K0 plus K2d, d has 2 in the forward and the aft side. So, totally 4. So, 4 such equations, and just make graphs of those, make 4 graphs, and then you, now that is a problem. You are told that what will be the change in draft at if the something 400 tons is loaded at some point in the forward perpendicular. You see what is the distance of that loaded point from the center of flotation, number 1 point, read from the graph, that then you will get for unit weight what will be the change of draft, then you multiply by 4, you will get your total change of draft. So, that is the way in which you solve this using trimming tables or trimming graphs, that is the importance of these graphs. Okay. So, that kind of concludes our session on trimming. Next is a process known as Drydocking. So, what I thought is, first you have to have some idea of what is Drydocking. We in this course, of course, we are not concerned with the physical process as such, which probably you will do in other courses like maybe even marine construction and welding, you might do some of those structures of the, but we have to have some idea of what it is. So, we will take a look at that, some of these will explain. Now, Drydocking means that that every ship has to at some time get repaired, it has some work has to be done on it at some time or other. So, always the ship has to be brought to land or to the shore at some point or other, okay. And therefore, there are different ways. Obviously, ship is we are mostly concerned with what happens in the, we will be mostly doing the repairs on the, let us say, the underwater part of the ship. So, that has to be brought up. So, this is a way of doing that, that is what is meant by Drydocking. You are actually bringing the ship up to the shore, that is meant by Drydocking, and you do it when you are maintaining. In fact, there is a rule, SOLAS, right, they say that every ship has to be dry docked at least twice in 5 years, okay. There is a rule like that, that is a requirement. So, so that means at least 2 times it has to come every 5 years it has to do. Now, okay, now there are a couple of ways in which you can dry dock a ship. These are the 4 methods given here. The most common, which is or the most used, is probably called a floating dry dock, and something very similar to it is something called as excavated dry dock, which is also, it is almost the same as floating dry dock. We will see, we actually have some figures. Then there is a two other methods which are similar to it, which are called as slip method, and another is lift method. As you can see, patent slip and ship lift. These 4 methods are the ways in which you can bring a ship to the shore, just physical process. Let us see this. Now, instead of doing this, I will show you a picture. Oh, what is this? Okay. Actually, the figure is not very clear, but see this figure. it should, I think it's okay. What is usually a floating dry dock is it's really a box. Okay, this floating dry dock is actually a box which is open in one side. So what they do is, so as you can see, the one facing the seaway is open, the other three are closed, and it's floating. And let's look at the explanation. So we call these kind of we call these kind of structures as pontoons, and there are there are some walls, these kind of walls we call as ponsons. I mean, it's okay, it's just walls, there is nothing more than that. Now, so these you have this box, what they will do is, now this is inside, part of it will be inside water. What we can do is, I have already told you about the process of ballasting. The thing is, if you see the sides, the sponsons as they call, are filled with tanks. So when you ballast it, or when you fill it with water first, because of the weight, the thing will go down, and when you remove the water, when the valves are open, due to ballasting, it goes up. Okay, so it can either go down or go up, it can sink, or so you bring the ship, there are rails and different kinds of equipments are here. You bring the ship here into the, first it is sinking, it is in a highly sunk condition, the ship comes and stays over, and then you lift it up, that is all. Ballasting, the whole thing is lifted up and you just bring it out of water, and this is known as a floating dry dock. It's, in fact, India also has a floating dry dock in many places. One of the main thing is, there is one in Andamans, dry dock of the Navy. So the pumping of water is done with the help of ballast pumps, that is what, there are pumps on it, which are located in the sponsons on the sides, and of course, there are cranes and all that to, if you have to move something on the ship. Now, these are some things, just if you just for your information, there are something known as keel blocks, side blocks. Let's like this. Okay, this figure is not at all clear, but if you look here, it's better. See, these are the known as keel blocks. I mean, it's like the block on which you finally place your ship. So you bring the ship, and it will finally come to rest on that block, keel block, and some other, I cannot see anything here. Some other things, there are rails and side sponsons. Anyway, these just to so these are two pictures. This picture actually, I think you can understand what it is. You can see the four sides. One side is closed on the close to the shore. So ship comes there, then it is either first it will be in a sunk condition, then it will be lifted up. As you can see, when it is lifted up, the ship will come out. Actually, it's not very clear if there is a ship there or not, but I don't think there is a ship there. Is there a ship there?
Yeah.
No, right? See, some people are saying yes, some people are saying no. Actually, I am also not sure. But
sir, why do you need ballast pumps to pump out the water?
How else will you do?
Like it's open from one side. Like the ship is entering that box-like thing from one side. So when you lift it, automatically water is supposed to go out.
How will you lift it up? By cranes? No, that is not. That lifting up is the problem, no. So that is why you are doing ballast. You see, these tanks are there. When the weight goes out, it will lift up. Okay, then then next one is known as, this is the, till now that important thing is floating dry dock. Then the next one is called as an excavated dock. It's actually similar, as the name, as you can read it, it's very similar to a floating dry dock in that they close the door. It's not much of a difference. It's just the same thing. It's at a harbor usually. Now this is slightly different. Now this process is known as, this thing is known as a slipway. Actually, this figure says, also bottom is not very clear, but what it is it's really a rail kind of thing. So it's there on the shore. It's there like this. You can look at 1, 2, 3, 4. yeah, 1 is the topmost one. So, 1 2 3 4, you can see that comes here down here, it is attached to the ship, then this rail goes up, it goes up in this ramp, and the ship is moved up. This is a different kind of, this is not a dry dock, this is okay, it is a dry dock, but it is a different kind of, it is a dry dock, of course we are talking about dry docks only, but it is not a floating dry dock. Then so this is, it is called a slipway, in fact that is the name used for it, they call it, it is very much like a jack up system. You have you done something on nothing, elements of ocean engineering is next year. So, you will talk about the different types of systems in the ocean, like different instrument, different like oil rigs, different kinds of things, you will see these things. So, this gives you a figure of what happened, this is a real picture, it goes up, it is pulled up, and the last one is again something called as a ship lift method. As the figure, actually the figure will explain much better. Something is brought under, okay, the ship, in this case you have the ship here. See, this is the first case, the bottom one represents the initial case, that platform is brought under, okay, and then with a winch it is pushed up, it is jacked up like this, and the ship goes up, and you come here and you can make the repairs. So, these are what we are mainly, I mean the problems that we are going to be interested in this course is mainly associated with this, this thing, okay, dry dock, this, and this is roughly what we are talking about, what we mean when we say dry dock. Okay. So, now you have an idea. Now, let us go into the chapter as such. Okay. So, we are interested in this figure, let me draw. So, as we saw in the figure, what really happens is, you first the water level keeps falling, okay, because this thing is rising up, the water level around the ship keeps falling, and at one point the ship touches the block, we saw keel block. So, the vessel touches the keel block, and then of course, once the keel, it touches the keel block, then they bring in different kinds of clamps to make it secured. So, once that happens, it is okay. The problem is, when you are lowering the draft, means when the actually when this is lifted up and the draft is being lowered, I think somewhere in the statical stability, I think I talked about a change in draft, right, did it, do you remember? That is, when the draft keeps decreasing, you will see that the stability keeps decreasing, okay. And there was a region we defined as a critical draft, where the ship actually capsizes, okay. It becomes, means GM becomes negative. So, either I did, yeah, I think I did that. At any rate, that is known as a critical draft. So, as this keeps rising up, the point where the GM becomes negative is called as a critical draft. So, and then after, so it is important while you do the dry docking that you make these calculations, you make sure that the critical draft is not reached. Before it reaches the critical draft itself, the floating dry dock should reach the bottom of the keel block, in fact should touch the vessel, okay, the bottom of the ship, and it should clamp it. Once it is clamped, when you raise it, it does not matter, the ship will be in an upright condition, but till that keel block is reached, it is dangerous. If the, so for each, but in fact it is different for each ship itself. So, means as you can see, the critical draft depends on the hydrostatic data or the hydrostatic particulars of the ship itself. So
till the keel block reaches the ship, draft will not decrease.
which one? No, you make sure that the keel block is that high, that is the keel block touches the bottom the moment the draft reaches slightly above the critical draft. So, and then you clamp it immediately, or the meaning is that before the dry dock should be designed such that the ship should be safely clamped before the draft goes below the critical draft. That is what we are trying to do always. Okay. Then, so let us look now, I mean, in this here we are going to do the mathematics, all the details of the process. Okay. Now, this is the keel, this is the keel and keel block, this is the keel block and this is the keel, and therefore, you will have, now what will happen is that you can, as you can see, as the ship keeps decreasing, first of all its buoyancy keeps decreasing because the volume is decreasing, and the moment it starts reaching the touching the block, a reaction force comes from the block from the ground, okay, keel block. Now, it will become such that P, if P is the reaction from the ground, P plus the buoyancy is equal to the weight. Okay. It does not become buoyancy equal to weight now, it becomes P plus buoyancy equal to weight. That will be your equation of, therefore, you can get the buoyancy itself by when it is in a, when it has touched, the buoyancy itself can be given by W minus P, where W is the weight of the ship and P is the reaction from the keel block. Okay. So, from here you will have a force acting vertically upwards, P, the reaction from the ground, and let us say this is the water line. Then at some point you will have G, let us assume it is in the midship section, it is exactly there, it is G. Then at G you will have the weight acting vertically downwards, W, and somewhere in this region you will have the center of buoyancy, okay, it is actually vertical, not straight. Okay. So, this here you will have the buoyancy acting, which is given by W minus P, it is given like that. So, here you have the center of buoyancy B. Then now, as you can imagine, this this point is very much like the vessel heeling only, though it is in a different, there are some external conditions, it is just like a vessel in a heeled condition. So, this actually represents your meta center, okay, M, and now the resultant of this W minus P and P, which is a total of W, I am talking about the upward force, it will act at some point, means there is a W acting here up, there is a W minus P acting vertically here up. So, the resultant weight P plus W minus P will act somewhere in the center of gravity, okay, not center of gravity, not the center of gravity of the ship, I am saying at the center of force, center of gravity of the force, two forces are there, it is centroid, it will act there. So, somewhere here I will call it here, the center at this point another force will act, which is the W of weight W, and it is at the center, means you can very easily find like P into this distance will be equal to W minus P into this distance. So, it is just a centroid. Then, so this force W is acting here, and now this is the C. Now, you can imagine that this meta center M0 is now reduced to this point M1. So, it is a virtual reduction in your, this is what is happening, it is a reduction in your metacentric height, means the M is coming down. Initially the M which was here because just due to heeling it is m is there, but because of this p coming, because of it touching the keel block, another p coming and w minus p, because of the change or redistribution of buoyancy, the meta center has come down here to this point m1. Okay. And therefore, let us find the values, that is same thing we can let us take this distance to be x, this distance is x and this distance is y. Therefore, we can do that w minus p into y equals p into x. Now, this is k, actually this figure is not very clear, but still x, this distance x is this distance x. Okay. Just look at the figure, if you want I will draw this again maybe, yes. Or I will just keep this. So, this is k, this distance is x, this one, it is the distance between the vertical here, this p and this. So, this distance is x, you can see, let us complete this triangle, you will see that x is equal to k m1 sin phi, where the ship has heeled through an angle phi. Just look at the figure, okay, it is very m1, this is k, this is m1, k m1 sin phi is this distance x, it is because of this triangle, you can, it's one is 90 degrees. So, and similarly y is equal to, y is this distance, this distance m0 m, it is m0 m1 sin, this is phi, okay, this is the angle through which the ship has heeled, or the angle through which the ship is heeled at the time when the thing touches the block, the ship touches the block. Actually, that is called as a critical instant, I mean just a term in drydocking, these people call it like that, critical instant. That is when the, I mean the ship keeps rising, the moment at which the ship touches the block, that time is called critical instant. Then x is called as km sin phi, okay, x is km sin phi and y is m0 m sin phi. Now, if we just put in this equation, it becomes w minus p into k m1, I mean m0 m1 sin phi equals p into k m1 sin phi. Then therefore, w into m0 m1 minus p into m0 m1 equals p into k m1. This is just you remove the sin phi, cancel the sin phi, it becomes this, or w into m0 m1 equals p into k m1 plus p into m0 m1, or m0 m1, I mean m0 m1, m0 m1 is equal to p into km by w. Let us see, p into m0 m1 into km, is it km? I think. Why is it w, or is it w plus p, w minus p? Wait, m0 m w minus p, no? No, denominator seems like w minus p. Actually, yeah, I think it's w minus p. Otherwise, what will it be?
But I thought you added km1 and m0 m1 made it km0.
That also you can do. I think that's what they have done. Okay, you can do that. Km1 and m0 m1 can be added to make it km0. That is correct. Okay, p into km0 divided by w. That is the better. Okay, p into km0 by w. Okay, so this will give you a value. P is the or w minus p is the buoyancy. So, p is that change in buoyancy. from the weight difference between the initial displacement, and actually this P you can find in many ways. Obviously, there is no way to calculate directly reaction force from the ground. I mean, so the way is, if you remember when we are doing the hydrostatic curves, when we are doing the hydrostatic data, hydrostatic particulars and all hydrostatic curves, we did a curve between draft and displacement. There was a means every hydrostatic curve is between draft and something, okay, draft and TPC, anything, whatever it is, or draft and LCG, LCB, LCF, like that. So, if you, the first of these was a curve between the draft and del. So, what we can do is, as the draft keeps changing, if you just that we can directly measure, as the draft keeps changing, we can keep measuring the del. Mean, remember, for every ship there is a particular hydrostatic curve, okay, it's particular for the ship. So, it will be there in the ship mostly, and you can just look at that curve and you can say, for this particular draft, that is your value of del, that is your displacement. From that you can find P. Del is the buoyancy, from del you will get the buoyancy, which is W minus P, okay. I mean, you will get it in volume, you convert it to weight, multiply it with the density of water, you will get the weight, and W minus P you get, from that you get P. That is the way in which you usually measure P. That is, and once you have P, Km0 is the meta center, that is also a part of the hydrostatic particular. It is not particulars as such, but it will be part of your data. When you design a ship, your meta center you will have. Then W is the weight of the ship. So, this gives you a way of calculating the shift in the meta center because of the this thing Drydocking, okay, because of the change in the draft. Okay, then
So the first equations we used to derive this, that W minus P into Y is equal to Px, is that angular momentum conservation?
no,
No, like I mean,
linear, not linear. What am I saying? It the torque, total torque is 0, so that it will remain stable.
yeah. So what happened to the weight of the ship which was acting to gravity? We didn't consider that.
No, we are not. It's not that. I am just saying that. See, if there is a weight W acting, it's not about. Okay, it is that is, if there is a weight acting W1 acting at one point, and there is a weight W2 acting at D2, you can assume that there is a weight W1 plus W2 acting at its centroid, even if you understand. So, this is just for the buoyancy. So, there are two buoyancy forces, I mean two upward forces, one is from the buoyancy and one is from the reaction. So, if one is acting here at P, the other is acting W minus P, you can assume that a total W is acting somewhere in between. In addition to that, there is a weight W acting down. So, there are two weights, one acting up, one acting down. Is it clear? Okay. Then this will give you M0. Now, now what will happen is that as you keep increasing P, as the P keeps, once P becomes very high, you will see that means most of the weight of the ship is taken by the keel block now, okay. The buoyancy does not play much of a role. So, from that, when the draft keeps decreasing, then the buoyancy becomes smaller and smaller, and at one point, I mean after one point you can assume it to be very small and negligible. So, that is the way in which it proceeds. Now, this is another way of doing the same problem. Okay, let us see this. Okay, then Now, another way to look at this problem is there a problem? Yeah. Okay. That is, so let us consider the slightly extreme case when it happens, that is when once it has come down, the buoyancy is now very small. Okay. Now, so you have the weight P acting at the as before as the reaction force, the weight W acting here, then therefore, the difference in weight W minus P, 1 minute, and just is the new weight. Now, just 1 minute. W minus P is the resultant weight. It is like the now the final displacement of the ship. It is like the net displacement of the ship after it has touched. Okay, but let me clear it. 1 minute. That means first there is an upthrust and then there is a weight W. The resultant of this is weight acting through G1 above G0. Then 1 minute, I will just do this and then this is y and this is x, W into y is equal to P into x. Oh, this is x. 1 minute, I will explain. W into y is equal to distance x, W P into x is equal to W minus okay. Now, see there are okay. Now, that is you have the initial G0, that is the weight of the ship is acting there. Now, it is like there is these are weights acting down. As you know, if you add an additional weight, it is like a shift in G. Just like that, P at P, a force is added in the opposite direction of weight. It is not in the direction of weight, it is a reaction force in the opposite direction of weight, as a result of which also the G will shift. If it will go up, if it is a weight added, it will come down. I mean, it depends on where it is added. 1 minute, I think something is wrong in what I am saying. Just a minute. Wait, something I have to do some mistake I have made in this figure. Is either there is a mistake in the figure or I am making a mistake. In this case, the resultant of the upthrust P okay, I will just leave this for the timing. I will just do this problem. I will just read this and we will explain it next class. That is, you are told that a vessel is to be dry docked. You are told that it has a mean draft of 5 meter and kg equal to 11 meter, and you are asked to find. Okay, now that you find the Km, I mean you know that how to find the reduction in K, reduction in M or the decrease in M. Now, because of that decrease in M, you can find the new GM. Okay, so the question is, in this problem, first you have some data are given. We will see what data is given, that provided some hydrostatic data is given, you finally have to figure out at what point does the ship become unstable. So, the way to do that is to figure out at what point GM becomes negative, and to do that you have to figure out at what point to see GM, you have to find GM at each step, and that will be possible if you find out the position of m at each step, or the distance through which m is shifted. When you know the distance through which m is shifted, that is the that is the change in gm. I mean, that is a change in either km or gm. Okay. In our derivation there was no shift in g, there was a shift in m. So, that will, from that you can find the change in gm. Now, okay, this is first of all how you will get the data: draft, then displacement at 5 meter draft, then W minus P. Okay. See, what you have to do first is you will have a table like this. This is what is meant by hydrostatic data, like 5, or hydrostatic curves 4.5, 4, 3.5. See, for different drafts will be given, and for different drafts you need to find the different displacements. So, that it's just given, you have to read from the, means as the ship keeps coming down, the draft keeps changing, and as the draft keeps changing, what is P, or means you keep measuring W minus P, and from this you get P, that is the next column. So, it is like this, you keep reading 5, in this case it is given as 17,052 tons. So, in the initial case P is 0, P, because the change in buoyancy is 0, initial it is at the 5 meter draft. Now, it starts coming down, means the water level starts coming down and P starts increasing. So, as the draft keeps decreasing, the P starts increasing, and W minus P, I mean, you just read, it will become some value. Initially it will be 0, then this will become probably 15,240 like this, and correspondingly your P will become 1,800 and I don't know 12 like this. Okay. What? No, W minus P is 1,700. Why is it? Oh, W minus P is 17,052. P is 0, sorry, P is 0 and W minus P is 17,052, that is correct. So, this is the, so at each draft you find out the, you read it from the hydrostatic curve, you read out the value of P, and you keep doing this for each draft, and then actually since the time is up, we will stop here. Then from this you can find your different values of m, that is our next step, we will do it in the next class. Okay, thank you.